Okay, so last lecture we talked about one sorting routine, that is the heap sort, using the structure called heap. So today we will go through another sorting technique, because this sorting is dependent on another paradigm which is called the divide and conquer, and the sorting is called quick sort. Okay. Now the worst case time for this quick sort is order of n square, which is worse than the sorting routine which we have already seen. That sorting heap sort was taking only order of n log n. But still we will go through this routine because there are two reasons. One, we would like to know the paradigm which is called the divide and conquer. This is a algorithmic paradigm which is used to solve many problems. Okay. So what is the paradigm for this? Given a problem P, you divide the problem into two sub-problems. That is the divide part. Solve these two sub-problems, say P1 and P2, recursively. Then you combine these two solutions into the solution of the original problem. So this is the paradigm: divide and then you conquer. So most of the time the hard work is in the combined part. Okay. But in this case we will see that combination is not that much difficult for this particular quicksort routine. There is another reason why we want to learn quicksort, because quicksort in the worst case it may take order n square time, but on an average it works really better than any other sorting algorithm. Okay. Actually, even if you implement quicksort properly, even its performance program wise, like the time it takes, you will see it is performing much better than the other algorithms. Okay. Because the constants most probably are much less in quicksort. Okay. So let's go through this quicksort algorithm step by step. First of all, I will assume all the numbers have been given in an array. Okay. So the numbers have been given array A, which are in between P and say R. Okay. So basically what I am saying, we have been given this array, this location is P, this location is R, and the numbers are here. Okay. Why am I using this left position P and right position as R? Because there will be recursive calls. So I need in general indices. I cannot specify 1 or 2. Okay. So that's the reason. Okay. Now let's what is the algorithm? The major algorithm, as I told you, there is a divide step. So there is a divide. So what it will do, it will split the array between P and R into two. That's fine. If there is a mistake like this, you just ignore. Split APR into A PQ and A Q plus 1 R. Okay, you split it. We will see how to split this. So this is the divide step. Then you have to recurse. There is a recursion step. Sort A PQ and A Q plus 1 R recursively. Then you have a combined step or the conquer step. So in this case, this is trivial actually. This is trivial. You don't have to do almost anything, because you have got your left part sorted, your right part sorted, and the way we will split, all the elements on the right part will be always greater than the elements on the left part. So the combined step is trivial. You don't have to do anything else. Let's now go over each of these steps except this conquer step a little bit more details. So first we have to partition the array APR. So that's the most non-trivial step. Let's see how to do that. And I told you the way we will partition the array APR will be such that the left part will be smaller than the all the elements in the left part will be smaller than the all the elements in the right part. Okay. So here is the function. First, let me write down the function which is called the partition. Then I'll by an example show you how is it working. Okay. So you first write down this function. So this is function partition. It takes two arguments, two indices p and r. What we will do, we will use one element of this array as pivot. And the pivot will be in this case the leftmost element. So AP will be the pivot. Using this as a pivot element, we will split the array APR into two parts. So first we assign this pivot AP, and we will be using two indices I and J. I will show you how do they work. So initially I is P minus 1 and J is R plus 1. There is a loop here. Repeat J is equal to J minus 1. Basically you are moving the right pointer J to the left one by one position until AJ is less than equal to X. Okay. When AJ becomes less than equal to X, you stop. So all the elements, as long as they are greater than X, you move the pointer, right pointer towards left. Alright. There is another repeat loop. You do the same thing for the left pointer I also. So this time I will be what? I plus 1 until AJ is AI is greater than equal to X. Now if I is less than J, then when I and J has crossed over these two pointers, I was in the first place was less than J, now I has crossed J. If it happens, then if it does not happen, then you exchange AI and AJ. If it does not happen, otherwise else, if it has crossed, then you return partition. This is a function. So partition name is used as a variable. Okay. So partition is equal to basically J, and you exit. This is end if forever. Okay. So this is the entire algorithm for partition. Forever means this loop will continue as long as you don't exit. At some point of time you will exit. I am not exactly using while loop or this. It should be okay to you. Means once I give you this type of algorithm, you should be able to program it in say C language or Pascal or any other program. All right. Okay. Now let us see how does this algorithm work. I'll just take an example and show you how is it working. So here is the example. I'm just taking some numbers. Okay, so this is just an array example. So if you remember, what is our x in this case? So suppose this is our P and this is our R. So what is our x? X is 20. This is the pivot. And if you remember, I is set here in this position because I was P minus 1 initially. So here was I. And J was just here. If you go back to the algorithm, these are the two initial setting. All right. Now if you go back to the algorithm, what we will do, J will be decreased as long as the numbers are greater than equal to 20. So let's see, 47 is greater than equal to 20, so it will be moved here. 31 is greater than 20, it will be moved. 25 is greater than 20, it will also move. It will stop here. 3 is not greater than equal to 20. So it will stop here. Now the next other loop, I is equal to I plus 1, where will it stop? Not 21. 20 itself it will stop. It is greater than equal to it was. So 20 is greater than equal to 20, it will stop here. Okay. Then I is less than j, that comparison is true. Then it will be exchanged. So 20 will be exchanged with 3. So 20 will go out, 3 will come here, and 20 will go here. So this will be 20, this will be 3. Now again it starts. J is decreased, and the very first one is 2. That loop again starts.
Sir, doesn't it consider 20 again?
Let's see what it will do. Okay, right now it is the pointer j. So j is decreased by 1 and 2 is less than, so it will stop here. So it stops here. Now I is equal to I plus 1, it goes immediately to 7. Right? 7 is less than 20, it will move to 21. 1 is not less than 20, so it will stop here. Now I is less than j, both two repeat loops are over. So I less than j, then 21 and 2 will be exchanged. So these two will be exchanged. So 21 will come here, 2 will come here. All right. Now again, next time, now entire loop again starts, the two repeat loops. The first repeat loop j is equal to j minus 1, 1 is less than 20, so it will stop here. And what about I? 3 is less than 20, which is fine, 1 is less than 20, which is fine, 2 less than 20, 10 less than 20, 11 less than 20. The first time it will stop 51. Okay. And now I is still less than j, so these two will be exchanged. So 1 will be 51, 51 will be 1. Now again the entire loop starts. J will be this 22, 22 is greater than 20, it will move to 21, 21 is greater than 20, it will move to 61, which is greater than 20, it will move to here. Now it sees that it is 1, 1 is not less than 20, so it will stop here now, j, the pointer j. And what about I? I will move to this one, 61, and 61 is greater than 20, so it will stop here. And this time I is not less than j. And what did we say? If I is not less than j, you return the partition, the value of j, and exit. So the value of partition will be this j. So this is the partition value now. All right. And you can see all the elements have been arranged properly. All the elements to the right are greater than equal to all the elements on the left. So partition is returning j like this. So if you take from P to J, all the elements from P to J will be less than equal to J plus 1 to R, the way the partition is working. All right. So that's the total algorithm now. You go back here. We split PR. What is Q? It will be APJ basically, or Q will be returned by the partition routine. So APQ and AQ plus 1, and recurse on these two, you will get the entire quicksort. All right. Now my question is, how much time does this partition routine take? How much time does it take? If you have an array of length n, how much time does this partition routine take? Order of n? Why? Right. It has checked for all the elements is not a very good logic. That is also not a very good logic. The logic should be that any element is scanned at most once or twice some constant number, which is true. The entire algorithm partition is moving two pointers, I and j. J is moving from right to left, I is moving from left to right. And the entire algorithm complexity is definitely determined by the total movement of this pointer. And what is the total movement of the pointer? At most, J can move, even if we are very pessimistic, it can move the entire length of the array, which is n. I can move also entire length of the array, but that will not happen. Actually, it will be less than that. Even if we are pessimistic, it is at most 2n, which is order of n. So entire partition routine, so this is order n time. Yes.
So we have not taken care of the array size here. Like when you say I equal to I plus 1, it might go outside the array and keep searching. You should take care of the boundary condition.
Yes, we have taken care of the boundary condition. It is PNR. PNR, and we have said I is equal to P minus 1, J is equal to R plus 1.
Yes, sir, but when you are repeating, like when you are moving to the left constantly or moving to the right constantly, you are just checking for the value of the element. The element might be outside the array.
But that you can, but it will never happen because already you have swapped this element and they are already less. Somewhere this J will stop. Like J cannot go move all the way down to the left because already X has been swapped with the element which is less than that. So that point it will catch. It cannot go beyond that. Just like it was happening in this example. In this example, J was stopped because 1 was there. Something else has been swapped. So it will stop there.
So suppose first element
is 20. Yes. If the first element is the
largest one.
First element is the largest one. At least J will stop at that element because it is less than equal to.
No sir, I will go on like on the right side. I
will stop at 20 itself first. And even if it happens, you can easily take care of this boundary condition. Just make a check whether it is less than P or greater than R. That's not the crucial point here. The crucial point of this algorithm that it is finding the proper partition in linear time. Okay. Now let us see what is the complexity of this entire algorithm. How do you express the complexity of this algorithm? So before I express the complexity of the algorithm, let me draw a picture of these recursive calls. Suppose initially there was 8 elements. I'm denoting each recursive call with a node in a tree. So its value was 8. Right. Then it got probably split into two parts. One is say 3, another is 5. Probably this 3 got into split into two parts. One is 1, another is 2, 2 again 1. When each element is 1, it will stop. Basically, it will not give any recursive call. Okay. Now this one probably got split into 1. This is say 4. This is split 1. This is 3. Say this is 2 and this is 1. This is 1. So these are the size of the recursive calls, number of elements on which it were called. Now we can see the total time on n elements depends on what? What should be the recursion here? Tn should be, what should be the recursion?
Sum of the two partition times.
Sum of the two partition times and number of levels. It's not the number of levels. First of all, you gave two recursive calls. You gave two recursive calls. What are the time for these two recursive calls? Suppose the partition was at the point q. One partition was having q numbers, another was having say n minus q numbers. So what should be the time for these two recursive calls? Right. So it should be tq plus tn minus q plus what? Other than these recursive calls, what were there? The partition time. Partition time was order n. So this is our recurrence relation for this time complexity of this algorithm. Okay. Now let us see what is the worst case behavior. So let me write it down again. Tn is equal to tq plus tn minus q plus order of n, and of course t of 1 is, I'm just saying 1. Sorry, yes, order of n. And I'm saying t of 1 is order of 1, I'm just writing as 1. Alright. Now, if the partition is very balanced, then you can see this tree will be a very balanced tree. Like 8 got split into 3, 5 or 4, 4. 4 got into 2, 2. Each time it was balanced partition. Then this tree, entire tree will be of height log n. If the tree is very balanced tree, then the height will be log n. And if you count each level, the total weight will be always n. Not more than n. Here 8, 8, this is also 8, this is also, it should be like this. So if there were log n levels and each level has order of n elements total, each level over all the nodes in that level, then total complexity becomes n log n. But it all depends whether the tree is balanced or not. It might very well be that the tree is very skewed one. What is the skewed tree? Then in that case the partition will just take one element in one partition, rest of the element in the other partition. It may be like as he was saying. Suppose the smallest element itself in the leftmost one, then you will see the leftmost partition will have only that element, all the other elements will have in the other partition. So in that case what becomes our recurrence? Tn is equal to t of 1 plus t of n minus 1 plus order of n, and t of 1 is 1 which I can neglect, so I can write this is t of n minus 1 plus order of n, because I can absorb this t of 1 in order of n. So what does it solve to? Tn is equal to Tn minus 1 plus order of n. What does it solve to?
1 plus 1 minus 1 plus
Order of n plus order of n minus 1 plus order of n minus 2, it goes up to a 1. So basically, if you unravel this recurrence, what you will get this will be equal to order of say 1 plus 2 plus 3 up to n. And you know this sum. What is this sum? N into, and what is the order of that? So in that case, there is the worst case behavior of quicksort, where you have only one element in one place, rest of the elements on the other place. And you should not be very specific about one element. It may be two element, n minus 2 element. That also will give you same thing. Anything constant, any constant, if q is constant, that's the problem. Constant, independent of n, you will have the same behavior. Alright? And as long as it is balanced, it need not be n by 2 all the time. It can be n by 3, 2n by 3. That's also a balanced criteria. But as long as this partition is dependent on n, it's alright. It's a fraction of n. Then the complexity will be n log n. So this is the worst case complexity, because nothing can be worse than this. And we have already seen the best case complexity is n log n. All right. Now let me go over this entire algorithm, but with a little bit difference. The difference is in choosing the pivot. What we have done so far, we have chosen the pivot as the leftmost element of the array. Suppose we don't do that. We use a random number, we generate random number between P and Q, or sorry, P and R, and choose this pivot randomly. Okay, see the difference now. I am choosing the pivot in the array randomly. And this randomness should not depend on anything. It should be, every number between P and R should be equally probable to happen. Now if you run the algorithm, suppose on certain input you have run the algorithm. It has taken some time, say t1. Suppose you run the algorithm again on the same input. What do you expect? Does the algorithm behave the same way as it was behaving previously? No. Because this time, since we are using a random number, the pivot probably have been chosen differently. So this is the difference between a deterministic algorithm and a randomized algorithm. So what is a deterministic algorithm? On a particular input, if you run the algorithm, it will behave exactly the same way. But a randomized algorithm, if you run the algorithm on the same input, different times it will behave differently. Alright. Now, if we can show that the most of the time of this randomization is good, the way you choose the pivot differently, if you can show by analysis that most of the time the randomized algorithm will perform very well, that means on an average it will perform very well. So your averaging is over the run now of the algorithm, over the different run of the same algorithm on the same. So when we say that the average case complexity of this algorithm is this, randomized algorithm is this, what does it mean? It means if you run the algorithm, most likely your complexity will be this much, whatever you deduced as average case complexity. But definitely it does not mean that it will always guarantee that much of time. It may run worse than that, but most likely that will not happen most of the time. Okay. That's the meaning of average case complexity for a randomized algorithm. So we are going to write now randomized quicksort. So this also gives you the paradigm. What is the randomized algorithm? You will see, you will hear this term, randomized algorithm. It's a very popular technique nowadays. This randomization gives you a handle on the algorithm for which you don't have to spend too much of gadgets in data structure or even in the complexity of the algorithm. But you get the performance very good. That's why people are after it. Like this quicksort is a perfect example for why randomization gives you good result. So what did we do? Instead of choosing the pivot only from the leftmost element, we just choose it random. Alright. So we will assume that a random number or random AB will generate a random number between A and B. That means every number, integers I am saying, every integers between A and B inclusive are equally likely to happen with random A. Or otherwise we can say that probability I is equal to random AB, it returns a number, is 1 over B minus A plus 1. All are equally likely. Because between A and B exactly this many integers are there inclusive. So all are equally likely to happen. So now let me write random partition. So function random partition PR. What you do? First you choose an I, which is a random PR. Then what you do? You exchange AP. You remember? AP was the element which we took as the pivot. So we exchange AP with A of I. Then you continue as it is. You just call random partition alright. So you just replace your partition routine with this routine, you will get a randomized quicksort algorithm. Of course, I have not shown it to you that it takes on an average n log n time. That we will go through. But you should remember this randomization means what? It does not depend on the input distribution. How the inputs are distributed, it does not depend on that. Because you are choosing randomly within your algorithm. It depends, the averaging is over the run of the algorithm. Same input, same algorithm, if you run, it runs differently. The claim is most of the time it is good. And since most of the time, most of the runs are good, it's very likely that the run you have chosen for this time is good. You have to be extremely unfortunate to have a run which was bad, because most of the runs were good. That's the power of randomization. It did not take too much of change in the algorithm. Only one call was there. And suddenly this gives you the power of Very simple algorithm with less time complexity. Is there any question on this? Yes.
So if we already give an array, is already sorted.
Yes.
This will take the same time as as my original pivot.
It will not, because your your pivot will be chosen differently. Which you remember with the random, it will choose any one of them as a pivot. It may choose, because any one can be picked as a pivot. It is equal probably.
But with a sorted array, like the situation will be same whether whichever you want you choose as a pivot.
So what?
Let me think a little bit. Will it be same all the time? If you take any pivot,
On both sides. Whichever one you take as a pivot. Whatever situation will be the same.
yeah, but how does it matter? Because no, situation will not be same, because your j will be returned differently. If it depends on your pivot, how the j is returned, the partition j will be returned differently to you. And if you see, if j is returned differently, your two components length will be different, and your complexity totally depends on that. Right? So his question was good, but you should be able to analyze it also, what is happening. Even if it is sorted, your j will be returned differently for different pivots. So partition will be different. But the point is, most of the time partition will be good. It doesn't matter whether it is sorted or not sorted or anything. It does not depend on the distribution of the input. We are not averaging over the distribution of the input. Probably you have already seen this average over certain things, but there you take care of the distribution, whether it is a Poisson distribution, random distribution, but we are not saying anything about the input distribution. We are randomizing over the runs of the algorithm. That is the key point here. Alright? So now we need to analyze this algorithm. The average case of this algorithm. I am not going over the worst case analysis of this algorithm. I would like to see what is the average case behavior of this algorithm. Alright. Now observe one thing. If AP was the leftmost element, the smallest element, then the partition will be 1 and n minus 1. Get convinced. If AP is the smallest element, then your partition will be, left part will be 1, right part will be n minus 1. Even if AP is the second smallest element, then also it will be 1 and n minus 1. So there are two cases for which it is 1 and n minus 1. For the rest of the things are the same. So let me write down the time complexity of this random partition. So what is the time complexity of the random partition? Tn is equal to T1. Remember, we are trying to do an average case analysis. So T1 plus Tn minus 1 is one case. I just take care of this one separately. When this AP is the smallest. Okay, and the rest will be Tq as it is, Tq plus Tn minus q, but this q can vary from 1 to n minus 1. Q can vary from 1 to n minus 1, q can be anywhere. So how do you average it out? You sum it, q from 1 to n minus 1. So you have now taken care of all the cases. How many cases are there? N cases. Right? Totally n cases. So how do you make the average then? 1 over? No, I already told you that there is a special case 1 to n minus 1 twice.
couldn't understand why if it is second.
Yeah, you have to go over the algorithm. Then you will see the partition will give you that way. Okay, so that's why it is so. Okay, now I have to divide by n, not half. If there are two cases, then you divide by 2. If there are n cases, you have to divide by n. That's the average case. So this is our complexity. What is it complete? Then I have to put order n, which is always right. So I need to analyze this part. So why don't you think over it, this analysis? In the next lecture, I will go over the analysis of this recurrence relation. Okay, I will give you the solution. We know that it should be n log n. In the next lecture, I will analyze it carefully and have the result. That n log n is the average case behavior of this quicksort. It is my experience actually, once I ran, I programmed both quicksort and randomized quicksort. Actually, I was having the experiment random quicksort, insertion sort, bubble sort and heap sort. It was the quicksort which was running best when n is quite large. Quicksort was better than anybody, and randomized quicksort was better than anybody. Generally, insertion sort works very well in the beginning, but it grows very fast. So whenever you need to sort a lots of numbers, quicksort is a choice, because on an average it performs really well in practice, and it's very easy to implement. Okay, so let's go over this analysis in the next lecture.